In the shadowed corridors of global trade negotiations, where economic leverage often masquerades as policy, a pivotal demand emerged in October 2025. China, the undisputed controller of over 90% of the world's rare earth processing capacity, required Indian importers to provide written guarantees that any rare earth magnets shipped from Chinese facilities would not be re-exported to the United States or used in ways that could benefit American industries. This stipulation, part of Beijing's expanded export controls, was framed as a measure to protect national security. Yet for observers in Washington and Silicon Valley, it signaled a deepening strategy to weaponize critical minerals, potentially severing supply lines to U.S. chip giants like Intel, Nvidia, and Qualcomm. Could this lead to a total blackout in semiconductor production, crippling the heart of American technological dominance? Or is it a calculated bluff in an escalating trade rivalry? To explore this, we must delve into the world of rare earth elements, trace the evolution of China's dominance, and examine how nations like India are being drawn into this high-stakes game, with consequences that ripple across the global economy. Let us start with the basics, presuming no prior knowledge of these essential yet obscure materials. Rare earth elements, often abbreviated as REEs, are a group of 17 metals found in the Earth's crust, including names like neodymium, dysprosium, terbium, and lanthanum. They are not particularly rare in terms of geological abundance. Deposits exist on every continent, but extracting, refining, and processing them into usable forms is complex, costly, and environmentally intensive. These elements possess unique magnetic, luminescent, and catalytic properties that make them indispensable in modern technology. For instance, neodymium is crucial for creating powerful permanent magnets used in electric vehicle motors, wind turbine generators, and hard disk drives. Dysprosium enhances these magnets' performance at high temperatures, vital for military applications like jet engines and missile guidance systems. In the semiconductor industry, rare earths are used in polishing compounds for silicon wafers, doping materials to improve chip efficiency, and even in the lasers that etch circuit patterns. The global supply chain for rare earths is heavily concentrated. Mining occurs in various countries: Australia, the United States, Myanmar, and others. But processing, the step where raw ores are separated and purified into oxides or metals, is overwhelmingly dominated by China. As of 2025, China controls about 87% of global rare earth mining output and over 90% of refining capacity. This dominance did not happen by accident. In the 1980s and 1990s, China invested heavily in rare earth infrastructure, offering low-cost production that undercut competitors. Western companies, facing stricter environmental regulations and higher labor costs, largely exited the market. For example, the Mountain Pass mine in California, once a major U.S. producer, shut down in 2002 due to competition and environmental concerns, only to reopen in 2018 with significant government support. China's state-owned enterprises like China Northern Rare Earth Group and China Minmetals receive subsidies, tax breaks, and preferential access to resources, allowing them to maintain low prices and control the market. This concentration creates vulnerabilities. Rare earths are not just industrial inputs, they are strategic assets. The term rare earths weapon refers to the potential use of export controls or supply disruptions as a tool of economic coercion or geopolitical leverage. China has employed this tactic before. In 2010, during a territorial dispute with Japan over the Senkaku Islands, Beijing temporarily halted rare earth exports to Japan, causing global prices to spike and prompting Japan to diversify its supplies. Similarly, in 2019, amid the U.S.-China trade war, Chinese state media hinted at restricting rare earth exports to the U.S., sending shockwaves through industries reliant on these materials. The U.S. Department of Defense, which uses rare earths in everything from F-35 fighter jets to night vision goggles, has repeatedly flagged this dependency as a national security risk. The semiconductor industry, the backbone of modern electronics, is particularly exposed. Chips power smartphones, computers, cars, and data centers. U.S. giants like Nvidia, which designs graphics processing units essential for artificial intelligence, rely on rare earth-derived materials for wafer polishing and magnet production and manufacturing equipment. A blackout, meaning a severe supply disruption, could halt production lines, delay product launches, and cost billions. For context, the global chip shortage of 2021-2022 caused by pandemic disruptions already cost the auto industry alone over $200 billion. A rare RTH blackout could be far worse, given China's near monopoly. India's involvement in this narrative adds a layer of complexity. As the world's most populous nation and a rapidly industrializing economy, India consumes growing amounts of rare earths for its electronics, renewable energy, and defense sectors. However, India produces minimal rare earths domestically. Its reserves are estimated at about 6 million tons, but extraction and processing lag far behind needs. In fiscal year 2024-2025, India imported over 54,000 tons of rare earth magnets, 93% from China, valued at about $1.7 billion. This dependency makes India vulnerable to Chinese export policies, but it also positions New Delhi as a potential player in reshaping global supply chains. To break down the events of 2025 step by step, we start with the broader US-China trade tensions that set the stage. In January 2025, following Donald Trump's inauguration for a second term, the U.S. administration announced aggressive tariffs on Chinese imports, including a 25% levy on electric vehicles and semiconductors, under the banner of economic liberation. Beijing viewed this as an existential threat to its export model. Rare earths, already a point of leverage, became central. On April 4, 2025, China's Ministry of Commerce imposed export licensing requirements on key heavy rare earth elements like terbium and dysprosium. These are critical for high-performance magnets used in EVs and defense systems. The move was a direct retaliation aimed at disrupting U.S. supply chains. Prices for these elements spiked globally, with dysprosium oxide rising 40% in a month. India felt the immediate impact. Its auto industry, aiming to produce over 5 million EVs by 2030, requires about 870 tons of rare earth magnets annually. Companies like Tata Motors and Mahindra faced delays as Chinese exporters halted shipments pending licenses. In May 2025, Indian officials quietly approached Beijing seeking exemptions. Diplomatic notes, leaked in June, revealed China's demand for guarantees that imported materials would not be re-exported to the U.S. or used in joint ventures with American firms. This was the crux of the rare earths weapon. By forcing India to comply, China effectively enlisted New Delhi in isolating U.S. industries. By July, the pressure mounted. U.S. chip manufacturers reported supply chain bottlenecks. NVIDIA delayed its Blackwell GPU shipments, citing material shortages in polishing compounds reliant on Chinese rare earths. Intel's foundries in Arizona faced similar issues, with wafer defect rates rising due to inconsistent supplies. The Trump administration responded with the Rare Earth Resilience Act in August, allocating $10 billion for domestic mining and processing, including reviving the Mountain Pass facility. But these measures would take years to bear fruit. India's response evolved. In September 2025, New Delhi approved a $1.8 billion scheme to boost domestic rare earth magnet production, partnering with Japanese and Korean firms for technology transfer. Yet, short-term needs forced concessions. On October 9, China expanded its controls under MOFCOM Notice No. 61, adding 5 new elements and requiring extraterritorial compliance. Any product containing even 0.1% Chinese origin rare earths needed Beijing's approval for export. This applied to Indian manufacturers using Chinese materials, effectively giving China veto power over India's exports to the U.S. In mid-October, Indian companies began receiving limited licenses, but only after providing written assurances against re-export to the U.S. This compliance, while pragmatic, aligned India with China's strategy, indirectly contributing to the weaponization of rare earths. By November, U.S. chip giants like Qualcomm warned of potential blackouts, production halts, if supplies dried up. A Reuters report estimated a 20% drop in global rare earth magnet exports from China, hitting U.S. defense contractors hardest. The F-35 program, requiring rare earths for radar and engines, faced delays costing billions. December brought a temporary truce. At the APEC summit, Trump and Xi agreed to delay further rare earth controls for 1 year, buying time for diversification. But existing restrictions persisted, and India's guarantees locked in, ensuring ongoing pressure on U.S. chips. Beyond these visible steps, hidden or less discussed factors reveal the strategy's depth. Geopolitically, China's moves are part of dual circulation, boosting domestic innovation while using exports as leverage. Less publicized is the environmental toll. China's processing pollutes heavily, but it externalizes costs, allowing low prices. For India, internal politics play a role. Modi's Atmanirbhar Bharat self-reliance push clashes with dependency, but EV ambitions targeting 30% market share by 2030 force compromises. U.S. vulnerabilities stem from offshoring. The CHIPS Act invests $50 billion in domestic fabs, but rare earths remain a choke point. Economically, shadow deals abound. Chinese state firms like China Northern Rare Earth Group control prices through stockpiles, manipulating markets. India's beach sand deposits, rich in monazite, remain underexploited due to regulatory hurdles and environmental opposition. The underreported aspect is espionage. U.S. intelligence reports Chinese firms embedding tracking in exported materials to monitor re-exports. Socially, in China, rare earth mining exploits minority regions like Inner Mongolia, raising ethical issues ignored in trade talks. Global implications are multifaceted. For U.S. chip giants, a blackout risks trillions in losses. Semiconductors underpin 10% of global GDP. NVIDIA's AI chips, reliant on rare earth polishing, could face shortages, delaying data centers and tech innovation. Broader economy suffers. EVs stall, renewables slow, defense weakens. Europe's similar dependencies accelerate de-risking via the Critical Raw Materials Act, investing €20 billion in alternatives. Emerging markets benefit unevenly. Africa, with untapped deposits, attracts Indian and U.S. investments, but debt traps loom if Chinese financing dominates. Trade wars escalate, WTO disputes rise, challenging rules-based order. Climate goals falter, rare earth shortages delay wind and solar deployments, missing Paris targets. Financially, surpluses from rare earths fund China's Belt and Road, expanding influence. Currency impacts, stronger yuan from controls, but U.S. dollar weakens if tech falters. Innovation bifurcates, Western R&D shifts to alternatives like iron nitride magnets but progress slow. In conclusion, India's reluctant alignment with China's rare earth weapon in 2025 through export guarantees poses a grave threat to U.S. chip giants, risking a total blackout in supplies. From April curbs to October expansions, Beijing's strategy exploits dependencies, disrupting global chains. While not immediate catastrophe, cumulative effects erode Western industry. For the U.S., urgent diversification, mining, recycling, alliances is key, though years away. India must accelerate self-reliance, balancing growth with sovereignty. China should consider cooperation over coercion, lest backlash isolates it. Globally, this highlights resource geopolitics dangers. Multilateral pacts for fair access could mitigate. As 2025 ends, thoughtful diplomacy, WTO reforms, tech sharing, ethical mining offers hope. The rare earth weapon need not destroy. It can spur innovation and equity, forging a resilient world where critical materials serve progress, not power plays. In interdependence, cooperation tempers conflict, ensuring technology's benefits for all. As the calendar turns to early 2026, the landscape surrounding China's export controls on rare earth elements and related materials has entered a period of pragmatic adjustment rather than escalating confrontation. The requirements imposed in late 2025, particularly the demand for end-user guarantees from importing nations like India that Chinese-origin rare earth products would not reach the United States, remain in effect, though implementation has shown flexibility in certain cases. Licensing processes, while rigorous, have allowed limited shipments to proceed for non-sensitive applications, preventing an immediate and complete disruption to global supply chains. U.S. semiconductor manufacturers continue to navigate constrained access to critical inputs, employing stockpiles, alternative sourcing, and process adaptations to maintain production continuity. Diplomatic engagements between major stakeholders have focused on managing tensions while pursuing longer-term diversification strategies. This phase of calibrated enforcement and adaptive response underscores the complexity of resource interdependence in an era of strategic competition. The mechanics of rare earth supply chains provide essential context for understanding these developments. Processing refined oxides into metals, alloys, and finished components, such as neodymium iron boron magnets, requires specialized facilities that combine technical expertise with environmental management capabilities. China's dominance in this segment stems from decades of investment in separation plants, magnet production lines, and downstream integration. Export controls operate through a licensing regime administered by the Ministry of Commerce, requiring applicants to submit detailed information on intended use, final destination, and downstream customers. For heavy rare earths like dysprosium and terbium, scrutiny is particularly intense due to their applications in high-performance systems. In early 2026, enforcement has balanced restriction with continuity. Approved licenses have covered shipments for civilian end uses in allied or neutral markets, while applications linked to U.S.-based entities or defense-related programs face prolonged review or denial. Indian importers, operating under the guarantees provided in late 2025, have received allocations sufficient for domestic needs in electric vehicles and renewable energy projects, though with ongoing reporting obligations. This selective approach allows China to maintain leverage without triggering a complete market freeze that could harm its own export revenues and diplomatic relations. U.S. industry responses have demonstrated resilience and foresight. Semiconductor firms have drawn on pre-existing inventories accumulated during 2024 warnings, extending coverage for several months of critical operations. Process engineering teams have qualified substitute polishing compounds and doping materials from non-Chinese sources, albeit at higher costs or slightly reduced performance in some cases. Recycling initiatives, recovering rare earths from end-of-life magnets and manufacturing waste, have scaled rapidly, with pilot programs achieving recovery rates approaching 70% for certain elements. Government support through the Department of Defense and Department of Energy has accelerated these efforts, providing grants and contracts to domestic processors. Diplomatic and commercial channels remain active. Bilateral discussions between the United States and China, often rooted through trade working groups or third-party facilitators, have explored confidence-building measures such as verified end-use monitoring in exchange for limited license approvals. Engagement with India has emphasized partnership in diversification. Joint ventures in beach sand processing and technology transfer agreements aim to develop independent supply capabilities over the medium term. Similar outreach to Australia, Vietnam, and African nations with rare earth deposits seeks to build resilient networks outside Chinese dominance. Less visible but significant factors continue to shape outcomes. Environmental and regulatory considerations influence alternative supply development. New mining and processing projects face stringent permitting and community consultation requirements in democratic jurisdictions, extending timelines but ensuring higher standards. Technological substitution research, iron nitride magnets, reduced rare earth designs, and alternative doping strategies receives increased funding, promising gradual reduction in dependency. Corporate supply chain mapping has become more sophisticated, employing digital tools to trace material origins multiple tiers deep. Economic interdependencies temper extreme actions. China's rare earth sector employs millions and generates substantial revenue. Prolonged restrictions risk domestic overcapacity and job losses if export markets contract sharply. U.S. semiconductor leadership supports global innovation ecosystems that indirectly benefit Chinese firms through software and design tools. These mutual interests create space for pragmatic management rather than outright confrontation. The global implications unfold across interconnected dimensions with measured intensity. For the semiconductor industry, constrained but manageable access to rare earth inputs encourages innovation in materials efficiency and process optimization, potentially yielding long-term competitiveness gains. Defense supply chains receive heightened priority, with stockpiling and alternative qualification programs ensuring continuity for critical systems. Broader economic effects include moderated inflationary pressures in green technology sectors. While costs remain elevated compared to pre-control levels, stabilized flows prevent sharp spikes that could derail renewable deployment targets. Emerging economies with rare earth resources gain leverage and investment interest, fostering development opportunities when paired with responsible governance. Systemic resilience emerges as a central theme. Diversified sourcing, recycling loops, and substitution pathways create multiple layers of protection against single-point failures. Market mechanisms, guided by policy incentives, direct capital toward sustainable and secure outcomes. In conclusion, the rare earth export control regime extending into early 2026 represents a sustained but calibrated application of strategic leverage rather than an imminent total blackout for U.S. chip manufacturers. The requirements imposed on partners like India have complicated supply chains without severing them entirely, prompting adaptive responses that enhance long-term resilience across industries and nations. For the United States, continued investment in domestic capabilities, international partnerships, and technological alternatives remains essential to reduce vulnerabilities while preserving leadership in high-value innovation. For China, balancing legitimate security concerns with the benefits of open commerce supports both economic stability and global relatio. Enships, for nations like India positioned between major powers, pursuing self-reliance through diversified development offers a path to greater autonomy. Globally, these dynamics highlight the imperative for cooperative approaches to critical resource management. transparent standards, equitable investment frameworks, and multilateral dialogue that accommodate diverse interests. As supply chains evolve and technologies advance, the rare earth challenge can catalyze progress toward more distributed, sustainable, and secure systems. The path forward lies in recognizing interdependence as a source of strength, channeling competition into collaborative solutions that ensure essential materials serve shared advancement rather than division. Through foresight and mutual accommodation, the risks inherent in resource concentration can be transformed into opportunities for resilient and inclusive technological progress. As the calendar advances into the second quarter of 2026, China's export control regime for rare earth elements and related materials has settled into a pattern of selective and sustained enforcement. Licensing decisions continue to reflect a case-by-case evaluation, with approvals granted for shipments destined for civilian applications in markets not directly linked to U.S. defense or semiconductor production. Shipments to India, for example, have proceeded at volumes sufficient to support domestic electric vehicle assembly and renewable energy installations, albeit under ongoing monitoring and reporting obligations. U.S. semiconductor manufacturers have adapted further by qualifying additional non-Chinese suppliers, scaling recycling programs, and optimizing material usage in fabrication processes. Diplomatic and commercial channels remain open, with working-level discussions exploring pathways toward greater predictability in licensing while preserving each side's core interests. This phase of managed restriction and incremental diversification illustrates the intricate balance between strategic leverage and economic interdependence that defines the current rare earth landscape. The operational reality of the controls can be understood through the structure of the licensing system itself. Applications submitted to the Ministry of Commerce require detailed documentation, including end-use certificates, supply chain maps, and declarations of final destination. For heavy rare earths, elements such as dysprosium, terbium, and yttrium, additional scrutiny applies due to their specialized applications in high-temperature magnets and defense systems. Approved licenses often include conditions that limit resale or re-export, enforced through periodic audits and traceability requirements. In practice, this creates a filtering effect. Shipments to neutral or allied markets face fewer obstacles, while those with traceable links to restricted entities encounter delays or denials. The result is not a complete cutoff, but a deliberate constriction that raises costs, extends lead times, and forces downstream users to seek alternatives. U.S. industry has responded with a multi-pronged strategy. Leading chip makers have expanded strategic stockpiles, drawing on inventories built during 2024 and 2025 when early warning signals were clear. Engineering teams have accelerated qualification of substitute polishing slurries and doping compounds sourced from Australia, Vietnam, and domestic facilities. Recycling efforts have gained momentum. Programs recovering rare earths from discarded hard drives, electric motors, and manufacturing scrap have reached commercial scale in several locations, with recovery yields for neodymium and praseodymium approaching 60 to 70%. Government-backed initiatives, including funding from the Department of Energy's Critical Materials Institute, have supported these developments, providing technical assistance and matching grants to private sector partners. India's position in this equation continues to evolve. The guarantees provided in late 2025 have secured access to sufficient volumes for domestic needs, particularly in the electric vehicle sector, where India aims to achieve 30% market share by 2030. At the same time, New Delhi has accelerated efforts to develop independent processing capacity. Projects in Odisha and Andhra Pradesh leveraging monazite-rich beach sands have moved from feasibility studies to pilot production, with technical assistance from Japanese and Australian partners. These initiatives, while still several years from full commercial scale, signal a long-term intent to reduce reliance on single-source imports. In the interim, Indian manufacturers have diversified procurement channels, increasing purchases from Myanmar and Australia to hedge against potential tightening of Chinese controls. Diplomatic engagement has followed a pragmatic course. Bilateral meetings between U.S. and Chinese trade officials, often conducted in third countries, have focused on technical issues such as verification procedures and license processing timelines. Similar discussions with Indian counterparts have emphasized collaboration in mining and processing technology. Multilateral forums, including the Minerals Security Partnership and the G7's Critical Minerals Working Group, have advanced coordinated investment in non-Chinese supply chains, targeting projects in Canada, Greenland, and Africa. These efforts aim not to displace China, but to create redundancy and resilience across the global rare earth ecosystem. Several underlying dynamics merit attention. Environmental and social considerations shape alternative supply development. New mining operations in democratic jurisdictions face rigorous permitting processes and community consultation requirements, extending timelines but ensuring higher standards. Technological substitution research, exploring reduced rare earth magnet designs, alternative polishing methods, and synthetic substitutes, continues to receive increased funding, promising gradual reduction in dependency over the medium term. Corporate supply chain resilience planning has become more sophisticated, employing digital traceability platforms to monitor material origins and mitigate risks from single-source reliance. Economic interdependencies continue to exert a moderating influence. China's rare earth industry generates significant employment and export revenue. Prolonged or overly restrictive controls risk domestic overcapacity and market share erosion if alternative sources gain traction. U.S. semiconductor leadership supports innovation ecosystems that indirectly benefit Chinese firms through software, design tools, and global market demand. These mutual interests create incentives for pragmatic management rather than outright rupture. The global implications continue to unfold across interconnected domains. For the semiconductor industry, constrained but manageable access to rare earth inputs encourages innovation in material efficiency, process optimization, and recycling, potentially yielding long-term competitiveness advantages. Defense supply chains receive priority attention, with stockpiling and alternative qualification programs ensuring continuity for critical systems. Broader economic effects include moderated inflationary pressures in clean technology sectors. While costs remain elevated compared to pre-control levels, stabilized flows prevent sharp price spikes that could derail renewable energy deployment targets. Emerging economies with rare earth resources benefit from increased investment interest, fostering development opportunities when paired with responsible governance and local value addition. Systemic resilience emerges as a central theme. Diversified sourcing, recycling loops, and substitution pathways create multiple layers of protection against single-point failures. Market mechanisms, reinforced by policy incentives, direct capital toward sustainable and secure outcomes. In conclusion, the rare earth export control regime extending through mid-2026 represents a sustained but calibrated exercise of strategic influence, rather than an abrupt or total disruption to U.S. semiconductor production. The end-use guarantees required from partners like India have added complexity to supply chains without severing them entirely, prompting adaptive responses that strengthen long-term resilience across industries and nations. For the United States, continued investment in domestic capabilities, international partnerships, and technological alternatives remains essential to reduce vulnerabilities while preserving leadership in high-value innovation. For China, balancing legitimate security concerns with the benefits of open commerce supports both economic stability and global relationships. For nations like India positioned between major powers, pursuing self-reliance through diversified development offers a path to greater autonomy. Globally, these dynamics highlight the imperative for cooperative approaches to critical resource management, transparent standards, equitable investment frameworks, and multilateral dialogue that accommodate diverse interests. As supply chains evolve and technologies advance, the rare earth challenge can catalyze progress toward more distributed, sustainable, and secure systems. The path forward lies in recognizing interdependence as a source of strength, channeling competition into collaborative solutions that ensure essential materials serve shared advancement rather than division. Through foresight and mutual accommodation, the risks inherent in resource concentration can be transformed into opportunities for resilient and inclusive technological progress. As the year 2026 reaches its midpoint, the framework of China's export controls on rare earth elements and associated materials has evolved into a stable and predictable regime, characterized by consistent application of licensing procedures and selective approvals based on declared end uses. The requirements established in late 2025, particularly the end-user assurances from importing nations such as India regarding the non-diversion of materials to restricted destinations, continue to govern transactions without significant escalation or relaxation. Shipments to compliant markets proceed at volumes calibrated to support legitimate industrial and civilian needs, while applications with potential links to sensitive applications face extended review periods. U.S. semiconductor producers have further refined their mitigation strategies, incorporating diversified sourcing, enhanced recycling loops, and material-efficient designs into core operations. Diplomatic and technical exchanges persist at multiple levels, seeking to manage frictions while advancing parallel efforts toward greater supply chain resilience. This period of steady-state management reflects the maturation of a complex interdependence, where strategic considerations coexist with practical economic necessities. The licensing system's day-to-day functioning offers insight into its balanced implementation. Exporters and importers submit comprehensive documentation, including supply chain traceability reports and binding declarations on final application. Approvals are issued with defined validity periods and quantities, often accompanied by post-shipment verification protocols. For medium and light rare earths used in consumer electronics and renewable energy components, processing times have standardized, enabling predictable planning for downstream manufacturers. Heavy rare earths with more specialized defense and high-performance applications remain subject to heightened scrutiny, resulting in lower approval rates for certain destinations. This tiered approach maintains pressure on targeted sectors while preserving broader market functionality. U.S. industry adaptations have deepened and broadened. Major semiconductor foundries have integrated alternative polishing compounds into standard production lines, achieving parity in yield and performance for many processes. Battery and magnet recycling consortia supported by public-private partnerships have expanded capacity, recovering significant volumes of neodymium, praseodymium, and dysprosium from end-of-life products and manufacturing waste. Design innovations, reduced rare earth magnet formulations and optimized doping profiles, have entered commercial validation, promising incremental reductions in material intensity without compromising functionality. Supply chain diversification efforts have borne fruit. Increased offtake agreements with Australian and Canadian processors, alongside emerging production in Vietnam and Africa, provide growing supplementary volumes. India's trajectory within this framework continues to demonstrate strategic pragmatism. Domestic processing initiatives have progressed to initial commercial output, with pilot facilities in coastal regions beginning to supply magnet manufacturers for electric vehicle and wind turbine applications. Technology transfer agreements with international partners have accelerated capability building, focusing on separation and alloy production. At the same time, imports from China remain essential for scale, governed by the established compliance mechanisms that ensure alignment with declared national priorities. This dual-track approach, short-term managed access combined with long-term capacity development, positions India to gradually reduce vulnerability while meeting ambitious electrification and renewable energy targets. Diplomatic and multilateral engagement has maintained constructive momentum. Technical working groups under various bilateral and regional formats exchange information on sustainable mining practices, recycling standards, and market forecasting. Initiatives such as the Minerals Security Partnership have coordinated investment in non-traditional supply sources, channeling capital toward projects with strong environmental and governance credentials. Discussions on verification and transparency measures, while not yet formalized, explore potential confidence-building steps that could ease licensing frictions over time. Several underlying currents continue to influence the overall equilibrium. Environmental stewardship has gained prominence in alternative supply development. New projects emphasize closed-loop water systems, reduced chemical usage, and community benefit sharing to meet international standards. Technological breakthroughs in separation efficiency and synthetic substitutes receive accelerated research funding, promising further decoupling from traditional rare earth dependencies. Corporate governance of supply chains has matured, with comprehensive due diligence and traceability becoming standard practice across major manufacturers. Economic interdependencies exert ongoing moderating influence. China's rare earth sector benefits from stable export revenues that support domestic employment and technological advancement, while global demand for clean energy solutions creates shared incentives for reliable supply. U.S. innovation leadership generates ecosystem benefits that extend beyond national borders, including through software platforms and design methodologies utilized worldwide. The global implications continue to manifest across interconnected spheres with measured progression. For the semiconductor and clean technology industries, managed access to critical inputs sustains innovation trajectories while catalyzing efficiency gains and material substitution. Defense and strategic sectors maintain operational continuity through prioritized alternative channels and stockpiling protocols. Broader economic effects include stabilized pricing dynamics in renewable energy components. While premiums persist relative to pre-control baselines, predictable flows support continued deployment scaling essential for climate objectives. Emerging economies hosting rare earth resources experience increased investment inflows, creating opportunities for value-added processing and local development when guided by robust governance frameworks. Systemic resilience emerges as the defining characteristic. Diversified sourcing networks, circular economy practices, and technological adaptation create layered protections against supply disruptions. Market mechanisms, complemented by policy coordination, direct resources toward sustainable and secure outcomes. In conclusion, the Rare Earth Export Control Framework extending through mid-2026 represents a sustained but carefully managed application of strategic policy rather than an instrument of comprehensive disruption. The compliance requirements integrated into trade with partners like India have introduced complexity without fracturing essential supply relationships, fostering adaptive responses that enhance long-term resilience across industries and nations. For the United States, persistent focus on domestic capabilities, international partnerships, and innovation in materials science remains vital to progressively reduce vulnerabilities while maintaining technological leadership. For China, aligning security objectives with the advantages of stable commercial engagement supports both national interests and global economic health. For nations like India navigating major power dynamics, balanced development of independent capacities offers a pathway to greater strategic autonomy. Globally, these developments underscore the potential for cooperative management of critical resources, transparent standards, equitable investment models, and inclusive dialogue that accommodate diverse priorities. As supply chains mature and technologies evolve, the rare earth challenge can serve as a catalyst for progress toward more distributed, sustainable, and secure systems. The path forward lies in harnessing interdependence as a foundation for mutual strength, transforming competition into collaborative advancement that ensures essential materials contribute to shared prosperity rather than division. Through sustained foresight and accommodation, the risks associated with resource concentration can be converted into opportunities for resilient and inclusive technological progress across the international community.